basically this population requires some kind of sites, and it can be arranged just like this, linear or one-dimensional format, or any kind of extension is possible. So 2D or any kind of lattice, or even graph or network in general. So almost synonym to each other, these two are. And the most essential part is we can actually fill out this one. And the most essential part is filling out or occupying this with a given probability. And this is a standard definition of the population, but perhaps more importantly, independent to each other. So for example, if you observe this consecutive occupied site, you may consider this as some kind of a correlation. You may suspect some kind of correlation. And depending on the perspective you will take, it can be considered as a correlation or no correlation, because in principle, the fact that these two consecutive sites are occupied is purely by chance. There is no organic relationship between these two. So precisely, this is a correlation by chance. But the very essence of population is this kind of correlation. Even if these are correlated by chance, we are focusing on this kind of correlation, or the population in general, meaning that going through from the left side to the right side, or any kind of occupation, is actually there's some kind of emergent behavior from this probability. So by chance or by emerging of some kind of non-trivial correlation, and this is not necessarily described by the totally smooth or analytic function. There can be some kind of singularity. And one nice thing about one-dimensional population is that it's kind of simple to describe. You can just write down the probability. But one unfortunate thing, or the fortunate thing, depending on the perspective, is that the only singularity occur at this very particular point. This P, the occupation probability equal to unity, where it's a trivial point, because as you can easily guess, if the occupation probability become unity or 1, it's just a trivial situation where all of the sites should be occupied. But interesting thing is happening when the parameter P approaches 1 from below. Of course, we cannot approach 1 from above, because this is a probability. So there's some kind of a interesting behavior is happening. So this is a very, as I already mentioned, this is not quite difficult to follow if you just follow the logic of the one-dimensional population. So yeah, according to this logic, for us to have a cluster with the size S, we have to have this cluster of size S. So there should be some consecutive probability to the power of S. Of course, we have to have this bulk of the bulk part of the site where all of these sites in the middle are occupied, and we have to have this boundary with this. But for a given P, this is actually constant, so the most important part is this. And one particular way to rewrite this P to the power of S, this looks simpler, but if we can start to write down, is a intentionally more complicated way. We can interpret this P to the S power as an exponential function with a characteristic size with this S sub psi. And this is actually given by this, because of this property, because of these mathematical properties, you can write down like this. And most interesting part is that this particular characteristic cluster size actually diverges as P goes to 1. So because it's a form of the -1 over 0 minus, so it actually should goes to plus infinity. Yeah. So that means that it's also intuitively understandable, because that means that as we approach to this particular singular point, the characteristic scale or the possible maximum length of the occupied size should diverge to infinity as well, because it's right before we approach or right before we reach this real trivial point with the probability 1. When we talk about this concept of phase transition, we usually take this approach. There is some kind of control parameter, such as temperature or external field or the level of noise, which is actually very similar to the notion of temperature anyway. And we have some kind of two types of phases here. And usually, this is phase 1, and this is phase 2. And then there must be some kind of transition point here. Transition point. Of course, the famous notion is the transition between liquid and gas or liquid and solid. And that would correspond to the situation like ice is melted to the water at the 0 degrees Celsius or something. And particularly, this is also called a critical point, but only for the continuous phase transition. So this is a typical picture of the phase transition. And all kind of some mathematical singularity and power law dependency occur near this transition point or the critical point. But one particularly peculiar thing about this one-dimensional percolation is that the only control parameter is, of course, the occupation probability. But from P 0 and 1. So since this is a probability variable, the only allowed position for the control parameter is somewhere here. And one interesting thing is that all of these phase here and So this is a phase 1 or non-percolating phase. But the problem is that this percolating phase is actually phase 2. And I use this double quotation because this is of course this is some kind of phase, but actually this correspond to a single point. So it's a singular point, but single point as well, where p equal to exactly 1. So in contrast to the conventional notation or conventional notion of phase transition, this one-dimensional percolation is this peculiar behavior. The second phase, or this percolating phase, is composed of a single point, not some bulk of the control parameter. So many of the conventional properties or conventional languages we can use for the continuous phase transition actually break down here. So in terms of a mathematical treatment, it is easier. But in the conceptual way, in terms of this phase transition concept and in the language of the statistical physics, this is a quite peculiar one. So it's not quite easy to grasp about the whole business of a phase transition and other things.